Gibson here. Today we're going to continue our lesson series in linear motion and specifically look at motion with acceleration in greater detail. So the objectives that we've already talked about are how did we define acceleration and gave examples of its units. What we're going to focus on now is how do we describe the motion of objects in free fall. And then the last part is to be able to use equations to determine the speed and distance that an object has fallen at any point in its free fall. And then we'll look at some other types of problems where we can apply a set of equations to help us analyze motion. So if an object is falling in the presence of gravity, it will accelerate at a constant rate of 9.8 meters per second squared. Okay, remember the units that we talked about in the last lesson of acceleration, right? It's the rate at which velocity changes. So any object that free falls in the presence of Earth's gravity will always accelerate at this rate. And it's not dependent on the object's mass, right? So a heavy object versus a light object, or I should say an object with small mass versus large mass, they will both fall at the same accelerated rate. Now, the one exception to that is you've probably seen if you drop a lead weight and a feather together, the lead weight will probably reach the ground before the feather. But the reason is because the feather has greater air resistance, right? So it will have some resistance to that acceleration due to gravity and fall at a slower rate. But if you drop those two objects in a vacuum with no air, they would fall at exactly the same rate of acceleration. All right, so we have our bungee cord jumper here. Let's let him go and see how this acceleration due to gravity applies, okay? So what we're gonna do is take a snapshot of his position after each second, right, of free fall, okay? And then you can see now he's bouncing up and down at the end of his bungee cord. So the first question we want to answer is what is the bungee jumper's velocity at these different time periods? Okay, now we're going to try and fill out this chart here. So the first thing that we notice, right, is that for the acceleration, notice that it's constant. And for the problems we're going to do in the lesson, we're going to round off that 9.8 meters per second squared to 10. Okay, that'll be fine for our calculations and kind of keep the numbers simple. Okay, so what we want to do now is saying what would be his velocity after each second of free fall. So at 0 time, when he was at the top of his bungee, right, his velocity was 0. But then once we released him, he began to accelerate. So how fast would he be going after 1 second? Well, we know that every second he's going to speed up by 10 meters per second. So at the end of 1 second, he'll be going 10 meters per second. At the end of 2, 20, at the end of 3, 30, etc. Okay, so this is pretty straightforward. Basically, we can find the velocity of an object in free fall by multiplying the acceleration times the time. So here's our first equation that we can use to describe velocity. Now, we derive this for free fall, but it applies to any type of motion where we have constant acceleration. So to find the velocity, it's equal to the initial velocity. So the V0 stands for initial velocity. And then we add to that acceleration. Excuse me. Acceleration times time, okay? And in this example, at our time equals 0 at the beginning, right, he had 0 velocity. So we really just had to multiply the acceleration times the time. Now, the little x in the subscript just means that the velocity and acceleration and initial velocity are all in the same direction. You think of an XY coordinate system, okay? If we were to be real accurate in terms of free fall, we probably describe that as in the y-axis, the vertical, right? So we could put y's there. But this equation is just meant to show that velocity and acceleration are in the same direction, right? We're still working with one-dimensional motion here. All right, let's try and answer the next question about displacement, right? We've answered how fast, but now how far will he fall after each second? So the way we're going to do this is kind of a manual method, but we can use what we've already learned about calculating average velocity. So what is the average velocity during the first second? Well, we know he had a starting speed of 0, an ending speed of 10. So what's the average speed during that time? Well, how do we find the average? We simply add two numbers and divide by 2. So his average over that first 1 second is 5 meters. So how far did he travel? What was his displacement? Well, 1 second, right, times his velocity would give us his displacement. So if we multiply that, we would see at the end of 1 second, he had gone 5 meters. Okay, so let's do the same process a couple more times. How far is he going to travel now? The question is during the second. Okay, so this is not total distance yet. We're just trying to figure out how far, right, he's going to travel in this second over here. Okay, so let's do the same thing. He had an initial speed of 10 meters per second. His final speed at the end of 2 seconds was 20. Therefore, his average was 15. So he traveled an additional 15 meters. Now, we have to take that 15, right, and add it to the 5 that he's already traveled in the first second. So we get 20, okay? All right, and so on. Let's do this one more time here for 3 seconds. So we start at 20, we end at 30, that's an average of 25. So he's going to travel an additional 25 meters. So we add that to the 20 he's already traveled, and we get 45. Okay, so can we recognize a pattern here? Is there an equation we could use to come up with this? Now, this one's not quite as obvious as the equation we had for velocity, right? But here's the other values we would get for 4 and 5 seconds. But here is the equation that we can use to get displacement with constant acceleration. Okay, so this again applies for free fall or any motion where we have constant acceleration. Now this looks a little complicated, but two of the terms here are if we have either an initial position that's different than 0, or we have an initial velocity that's different than 0. Okay, but in many of the problems that we're going to be working with, our initial position will be 0, so we can cross out that term. And if we start from rest, our initial velocity will be 0. So often, all we need is this term right here, 1/2 times the acceleration times the time squared to be able to calculate the displacement. Okay, what is the change in their position based on the acceleration and the amount of time that they've been accelerating. So we have two equations. Let me go ahead and clear my annotations. We have two equations that I've given you for motion. Okay, now we derive them looking at free fall, but they apply to any motion with constant acceleration. So notice that's the big requirement here. And all the problems we'll be doing in AP Physics will be constant acceleration problems. If the acceleration rate itself is changing, they get much more complicated. And so we'll leave that to a college level physics course, okay? So here's the motion or equation for displacement, the one we just saw. Here's the equation for velocity. Okay, that's the one we first derived. And then I'm going to give you one more equation. I'm not going to go through how we derived this one, but it's gives us, notice, displacement and velocity using initial and final values and acceleration, but notice there is no time in this equation. So this equation often is useful in solving problems where we don't have any time information. Let's say we know the velocities and the displacement, and we want to find the acceleration, but we have no time information. So this one is helpful. But these are the three motion equations that we'll be using for the next week or two here as we work on motion problems. So let's look at some examples here. And before we jump into examples, I want to lay out a problem-solving strategy for you. And this will be very important for you to develop a method, right? A step-by-step method how you solve these problems, okay? And so here are the steps that I would recommend. If you're given a problem and there's not already a diagram or picture, it's always helpful to draw out the picture, right? Understand what's happening. If it's motion, you know, what's the reference frame? What direction is an object moving? You could put all that information into a diagram and then start to label the data that you're given, okay? So that's kind of the next step. Identify and list the known information that you're given in the problem. And for motion problems, these are the types of information you'll be looking for, right? What is this position? Is it horizontal or vertical? What is the velocity, initial or final? Acceleration, right? For our problems, it'll either be 0 or some constant rate. Do we have information on time, right? And then again, are all these values initial or final values? So it's good to make a list of what do we know, and then what don't we know, right? What is the information that we're trying to find? Okay? And then once we look at what we know and don't know, then we have to look at which equation can we use to solve for the unknown. Okay, so which equation can we plug in the known variables for and then solve for the unknown? Okay, and you'll have those three equations to choose from. And then once you pick the equation, then go ahead and substitute in the known values. And in many cases, we'll have to rearrange the equation, right, to solve for the unknown. It won't always just be displacement or velocity that we're solving for. It could be time or acceleration. And then always look at your answer and check it. Is it reasonable, right? Does it make sense? If it's a vector quantity, is it positive or negative? What does that tell us about direction? All right, let's look at an example where we can apply this process. It says a ball is thrown down from a 70-meter tall tower with a velocity of 3 meters per second. What will be its position after 3 seconds? All right, so first, right, is to draw a picture. So here's our ball falling at 3 meters per second, and we're releasing it from a 70-meter tall tower. And notice I put a little plus sign up here, so that reminds me that the up direction going to be considered positive, the down direction negative. So what do we know? Well, we know the initial velocity. It says it's being thrown down with the velocity of 3 meters per second, right? And how do we know it's negative? Well, it says down here. So we're going to enter that in as negative. What else do we know? Well, the vertical position, we'll call that y0. It's 70 meters. So it's starting 70 meters above the ground. We'll consider that to be a positive value. We know the acceleration in the y direction. If it's in free fall, it's negative 10 meters per second, negative meaning down. And we know the amount of time that it fell, 3 seconds. So what don't we know? Well, we're being asked to find its position at the end of 3 seconds. So what equation could we use? Well, we're trying to find position, so we can use our equation for position or displacement. And now we just have to put in the correct values, right, that are given and solve for x. We're calling it y because it's vertical, but the default form of the equation has x in it. All right. Oh, I did change it to y. Okay, so we're going to put in -3 for our initial velocity. We're going to put in 70. Are we going to use that information? Yes, because we know the initial position is already 70 meters above the ground, and the acceleration we know is -10, and the time is 3. Okay, so in this problem, we're going to use all three terms of the equation because we have some initial conditions that are not zero. All right, we plug all that in and we do the math, grab the calculator, and we find that at the end of 3 seconds, the object will now be 16 meters above the ground. So it will have fallen, what would that be, 54 meters, right, from its original position. But its new position will be 16 meters, okay? So a good example there of how to work through the process and figure out what equation we're going to use. All right, let's try one more problem here. What will its velocity be after 3 seconds? Okay, so we still have all the same knowns here, but the unknown has changed. We're now solving for velocity. So again, what equation would we use? Well, we'll use the equation for velocity. And in this case, right, we know that we have an initial velocity of -3 from the original problem. Our acceleration is still -10, and our time is still 3 seconds. Okay, so let's plug all that in. And if we do the math with our calculator, we see that at the end of 3 seconds, its velocity would be a -33 meters per second. Now, is that a reasonable answer? Well, we know since its acceleration, right, is -10 meters per second squared, or every second it's going to speed up by another 10. So if we're starting at -3, we're going to add -10 to that 3 times. And that's exactly what we got in our answer here. Okay. All right. One more problem. I'm going to leave this for you. I'll just pause this and then show the solution, but see if you can now figure out its velocity just before it hits the ground. So our final position now is 0 meters, and we want to know what its velocity is, the final velocity. So the equation now is going to be this one that has velocities and positions and acceleration, but no time, right? We're not necessarily interested in time here. So let's plug in the values. We have -3 as our initial velocity. Our initial position is -70. Our acceleration is -10, and our final position will be 0, right? If it hits the ground, we now have a position of 0. So we can plug all that in and solve for v squared. And we've got to obviously grab our calculator because we've got to take the square root of 1,409. But we find that our speed when we hit the ground, just that instant before we hit the ground, would be -37.5 meters per second. All right, that does it for this lesson, okay? You've been given the equations. You will find these equations on your AP formula sheet that is posted in Google Classroom. And the assignment I've given you for today is about 10 problems where you'll get lots of practice analyzing motion and answering questions about how far, how fast, how much time, using the motion equations, okay? These are just going to work out on your own piece of paper and then submit those. And definitely in our next class, we will spend some time working through those problems together. All right, that's it. Thank you.